In this video, we're going to look at what I think is an interesting property in Pascal's triangle. Here's a formula that we're going to illustrate in Pascal's triangle, and it will leave you saying that's pretty cool, or at least in my opinion. I accidentally discovered this when I was doing some research in sequential binomial testing. Now, I actually thought it was new, and then discovered it's a quite old theorem, and here's one reference for it. But I still haven't seen it tied into Pascal's triangle. So that's what I want to show you. And I'm not saying that this is new. I'm just saying I haven't seen it. So let's quickly look at Pascal's triangle. Now, a lot of times you see it more in a equilateral type triangle, starting to peak and then spreading to the left and right. And I'm left shifting it so the property is sort of highlighted. And you'll see what I mean in a second. But this is row 0, row 1. And the way that these numbers are generated is the 1 always comes down, and then you take these two and it goes here. Now for here, the 1 comes down, 1 plus 2 is 3, 2 plus 1 is 3. Now we start here, 1 comes down, 4, 6, 4, and it just repeats. Now to use the formula on the first page there, you place an X anywhere in this triangle, anywhere. So let's say we put an X on this 35. Then what's going to happen is we're going to add the numbers to the right, and we're going to add the numbers above it in a special way. So here's the X that I wanted to place on the 35. And if we add these numbers, which equals 64, and then these are the coefficients in Pascal's triangle, and we take it times coefficients of 2, but we always start at 0. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and then when we run out of numbers, we stop. So when you add these, it equals 64. It's the same number. Let's place an X somewhere else. Let's say on this 7 next time, right? And so if we look at you can still see the triangle. So the 1, the 35, this was the 35, 21, and the X goes on the 7. So we add these numbers, which is here, which is 21, and then we add the numbers in the triangle above it, but we take each times a coefficient of 2 to the 0, to the 1, to the 2, to the 3, to the 4, 2 to the 5, and then those numbers equal the numbers to the right. So the numbers to the right equal to the numbers above it. And that the X can be placed anywhere in the triangle. That's what's kind of cool. Now, the next illustration is actually an illustration of a very famous formula on powers of 2. So let's place an X anywhere in the first column here, in any row. And let's see what I do. I just place it here, but it really could be anywhere. And so we add the numbers to the right, which is 15, and then to the 0, to the 1, to the 2, to the 3, we're out of numbers, we stop. And so when we add those, we get 15. So it really literally works anywhere in the triangle. But this particular one, when an X is in the first column, it's part of a much, much larger theorem. And it's the powers of 2 theorem. 2 to the n minus 1 is equal to 2 to the 0 plus 2 to the 1 all the way to 2 to the n minus 1. And that's kind of cool. So this is a special case of the theorem that we posted on the first page. But you can see that if you add that should have been a 35. I have to fix that. But if you add the numbers in any row, it's always 2 to the n. That's the number. But when we're placing an X in the first one, we're not summing that one. So that's the minus 1. And then we're just adding, powers of 2 essentially. And that's pretty cool. Anyway, it's a neat little illustration of that theorem in Pascal's triangle. And this next section is a little proof of it. I'm not going to go through it, but I'm going to scroll through it slowly for those that are interested and want to go through the derivation. Some may want to stop at this point. but it's a proof of this equation that we posted. That's an old equation. And we'll do it by mathematical induction. So first we're going to have two base cases, at k equal 1 and k equal n. And these base cases happen to be true for all n. So if we let k equal 1, and again, I'm not going to go through this. You can pause and go through it. We get these equations, and so they do equal. When it's n, they end up equaling. Now and then for any n, we assume it's true for k, and we're going to show that it must be true for k plus 1. And so here we repeatedly use the sum of binomial coefficients. So this binomial coefficient is actually equal to the 2. Then we distribute the sum, and we get this. And then we just repeatedly split this first coefficient again, distribute, and just rinse and repeat until we end up with this equation. Then we re-index it. So essentially all these sums start at k, and then they go to k, k plus 1, and then all the way to n minus 1. This we make this sum of sums into a double sum. We switch the order of summation and then split, and then we get some simplifications down to these three terms. Well, if you count that as one term, 2, 3. And then we're going to use the mathematical induction step on this. And then we're just going to combine those into one sum. And what is interesting is then when we add a term, or we subtract a term, or take away a term, that's this one. But what's interesting, these two add to 0, and it's called the hockey stick property of Pascal's triangle, which is kind of neat in itself. And so after applying the hockey stick property, then what's left is what we wanted to show and wanted to prove. Well, anyway, I think it's such a neat little theorem in Pascal's triangle that it was worth showing you. So I hope you enjoyed it. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.